All right, I'm starting right out of the gate today because I have a lot to cover and I understand your wrist will get tired from writing. The idea is, if this recording, the universe willing, this recording works out, that all this work I'm doing will be recorded. I don't expect everybody to get every single word I say today. I'm going to give you a lot of material, but I'm going to try to record as much as I can, get as much as I can available to you to watch back and have as many examples as possible to learn the material. So I'm saying right off the bat, I don't expect everybody to get this first time. The collaborative exam will help you reinforce the material, but there will be a lot of material to cover. And just by sheer volume of stuff you're gonna have to know, it's gonna be a bit of a busy day. Now, the good news is if I can get through this in time, which I'm optimistic I can, I have one of the best demos of the semester waiting right in that cart. So there definitely is a light at the end of the tunnel. Literally, it'll be a bright light, but a lot of heat and a lot of energy. All right, so this slide is just to remind you the idea of density. And density, of course, is how much mass you fit into a given volume. So if we have the same size volume like we have in these squares, if you have more matter in it, it's very dense. If you have little matter in it, it's not that dense. And gases are the least dense of the three states of matter that we've studied. But we can use the molar volume at STP, where 1 mole equals 22.4 liters of volume. Again, that's only at STP. We can use this relationship to quickly determine the density of a gas. So the idea is that gases are not very dense, and so their densities are in grams per liter. You're used to maybe like grams per milliliter for solids and liquids or cubic centimeter, but the idea is there's not very much matter in a space for a gas. So this is a better unit for measuring density than other states of matter. Now the idea is that 1 mole of a gas occupies 22.4 liters. That's any gas. But if you're talking about a specific substance, like the composition, 1 mole of anything will equal its molar mass. And that's that mass that's listed on the periodic table. So these are the molar masses. Now, since these two things are equal, I can establish that 1 mole will equal a certain amount of grams, its molar mass, and those same amount of grams will occupy a given volume at STP. And so what we can basically boil this down to say is that density is in grams per liters. The grams, well, that comes from the molar mass of whatever it is, whatever substance you're looking at. The liters come from the 22.4 liters per mole. So basically, to solve the density of any gas, I just need to divide its molar mass by 22.4 liters per mole. And I will be able to get the density. So what I've given you is just the proof, and now just the easy way to solve these problems. So you look at the compound that you're being asked to address, which is ammonia, and then you need to know its formula, NH3. Now, last time we talked about how to look up the molar mass. I'm going to add up 3 hydrogens right here and 1 nitrogen. And so I would determine that the molar mass of ammonia would be 17.03 grams for every mole. All right, well, we're going to divide that molar mass by 22.4 liters per mole. So again, at STP, 1 mole of NH3 will have a mass of 17.03 grams, and it will occupy 22.4 liters. So the grams, the per moles, cancel out, and we end up with grams over liters. So when we compute this, and hopefully you guys are checking my math, 17.03 divided by 22.4, I get that would be 0.760 grams per liter. Okay, so hopefully you don't need to worry about the proof other than just believing me that this works. You guys probably will find success just by using this formula. So here's another question. What is the density of fluorine gas at STP? So some of you are probably already on this. You know the idea is that the trick is fluorine gas is F2 because it's one of those diatomic elements. And so that means if you look at its molar mass here, it's basically 19. It's 18.9999. Its molar mass basically equals 38.00 grams per mole because it's 2 fluorines. So when we do the expression here to solve for the density, we take the molar mass and we divide by 22.4 liters per mole, the molar volume. So, that's liters per mole. Then the per moles cancel out and we have grams over liters. The molar mass divided by the molar volume equals the density. 38 divided by 22.4. And I get 1.70 grams per liter for fluorine. So you can see fluorine is going to be more dense than ammonia because it's a more massive molecule than ammonia. Okay, so hopefully those are pretty straightforward. Now, back in the olden days, they didn't have computers and sophisticated instruments to determine the identities of an unknown gas. So they had to rely on other means. So here's an interesting way that you could determine the identity, at least in terms of the molar mass. So if you know the molar mass, right? The molar mass is how many grams of matter you have in 1 mole. So this is the units of molar mass. So the idea is they would release a certain number of grams of a gas, and that obviously is the grams is there, the numerator. And then they would figure out at STP how much volume that gas would take up. And from that, the 10 liters at STP, they could calculate moles. So again, the question is asking for the molar mass of a compound. Molar mass is the grams of compound divided by the moles of the compound. It gives you the grams. We have to calculate the moles. And this will be similar to the problems you get on your exams. You're given the information that includes the grams, so you know the numerator. You have to solve for the denominator. So we need to know how many moles 10 liters of a gas would be. So we say, all right, at STP, 10 liters of any gas, well, 1 mole will be when we have 22.4 liters. So when we do this part, and again, I've done these calculations, many of them ahead of time just to save time. When you do this portion of the calculation, you'll find they have 0.44643 moles of the gas. And the reason I put the bar over the 6 is because this is good for 3 sig figs. But this is not my answer, so I don't want to round it. In fact, I kept some extra sig figs. I kept 2 extra sig figs. Even better would be if I went 10 divided by 22.4 and I left this whole number in my calculator. Right? This is the complete unrounded number. So what I need to do is divide this number into grams. So if you know how to use the inverse function on your calculator, great. If not, make sure you keep some extra sig figs. So 9.41. So I get the answer when I divide this into there, and I have 9.41 grams from the problem over this value, 0.44643. I get that will equal 21.1 grams per mole. So again, by this work, these scientists were able to identify the matter as having a molar mass of 21.1 grams per mole. So if you have an idea as to what elements could be there, or even if you have to take a wild guess, there's only so many combinations of elements that could have that mass. So it helps them identify what substance they're looking at. All right, so one more practice problem at this, since this is going to be the same way you'll solve these. Remember, when it asks you for anything, look at the units that you're going to need to solve for. Molar mass is grams per mole. So in these type of problems, they always give you the grams in the problem right there, 1 gram. Your job is to figure out how many moles that 1 gram will become. So those, again, you solve from the volume at STP. This is trickier just because it gives you the volume in milliliters instead of liters. But not that tricky because we've been doing this for a while. So if we have 985 milliliters, and milliliters is not the right unit, we need the right unit, which is liters. So we say 1 liter is 1,000 milliliters, and we convert to liters. All right, so now I'm in units of liters, and I say that I'll have 1 mole of this unknown gas, or 1 mole of any gas for that matter, at STP when it occupies 22.4 liters. So when I do this, I will get 0.043973 moles of the unknown gas, good to that 9 for sig figs. So once I know the moles of the compound, I have solved for the denominator. So I take my 1 gram, put it in the numerator, and I divide it by these moles. And again, I didn't round yet. I kept at least a few extra sig figs. And then I'm going to, and this is moles, and then solve that way. So 1 divided by 0.043973. I get 22.7 grams per mole. All right, so hopefully, even if you're not fully grasping what this problem is trying to accomplish, you recognize where you're going with it. These are the units you need. The grams will always be given in the problem. The moles, the denominator, you solve from the volume using the 22.4 conversion. Okay, so in the unlikely event that I have some time to spare at the end, I will come back and do some more problems. So I'm going to put this one on hold. There was no new ground to break with those problems. It was just more of the same. So let's move on to the newer topics to get them all covered. Percent composition of the Earth. This is percent by mass, grams. So this is the Earth. If you took the entire Earth and weighed it, and then let's say you weighed all the hydrogen that's in the Earth, it would be 1% of the Earth's total mass. However, hydrogen is the most abundant of all the particles. So if you counted them, hydrogen would be the most abundant. But this has to do with the fact that it's very light, so it therefore is only 1% of the mass. Oxygen is nearly half the mass of everything on Earth is oxygen. And then silicon, another quarter about. So 75% of the Earth is silicon and oxygen, or basically glass or sand. Those are the primary elements. Okay, but again, this is by mass. And what we're going to do is we're not going to talk about the composition of the Earth in this class. That would be a geology class. What we're going to talk about is the composition of chemicals. But it's the same basic concept. And the idea is when you have a mass percent equals grams of the part you're looking at divided by the grams of the whole thing, and then times 100 to make it a percent. So we're looking at a small portion relative to the whole thing. So like this pie chart, right? So this little piece of the pie represents hydrogen, that part relative to the whole Earth, including hydrogen. So again, we're looking at the little piece of the pie relative to the whole pie, and then making it a percentage. So when we're talking about mass in chemicals, we're looking up the molar mass. So the mass of a water molecule, H2O, equals 18.02 grams for every mole. So that's me rounding to the hundreds place, adding up 2 hydrogens and 1 oxygen for the mass of water. And now what we're going to do is figure out what percentage of that 18.02 grams is due to the hydrogen, and then the rest of it due to the oxygen. So I look at the gram of the portion I'm evaluating over the whole thing. So for hydrogen, I have 2 of them in the water molecule. And each one of those weighs 1.01 grams per mole. I'm going to see how many. I gave myself a few more sig figs on when I did the calculation. So 1.008 grams per mole. grams per mole. That's the mass of hydrogen rounded to there off the periodic table. So I want the mass of the hydrogen, or specifically two of them, over the mass of the whole water molecule, 18.02 grams per mole, and then times 100 to make it a percent. So when I complete that, I will get that hydrogen is 11.19%. All right, well now we need to also consider oxygen. So for oxygen, and I have two options. The first one is to do it the exact same way, where I take the mass of the oxygen relative to the mass of the water. So with water, I have one oxygen, and the oxygen weighs 15.999. So we compare the mass of that one oxygen to the mass of the water as a whole, times 100. And if we do that, we'd get 88.79%. Now, I'm sure there's some of you that are looking at this and probably want to point this out, so I'm sorry to take the wind out of your sails. There's another way I could have solved this, is I have to realize that 100% of water is 2 hydrogen and 1 oxygen. And if I figure out that the hydrogen is 11.19%, I could have easily have said that oxygen equals 100% minus 11.19%. That's another way I could have done it. Because, right, these numbers should add up to 100%. So if I figure out hydrogen, I could subtract the rest of it from 100% and get it that way. Now, so that's fine, and you'll get probably something very close to that, acceptably close to that. But notice how this kind of quite doesn't equal 100%, but it's close enough. And even if you subtracted it this way and solved it, it's going to be ever so slightly different than here, possibly. But the idea is it's close enough. And in a multiple choice test, if yours is 0.001 different than the answer, I'm not looking to have it be none of the above or anything like that. I'm looking to have you find the percentage that's the closest. Okay, so I'll do 2 more examples of these to drive the point home. You have to know the formula. Nitric acid is HNO3, because if you don't know that, you're not going to get liftoff. So we would quickly add up the mass of a hydrogen, a nitrogen, and 3 oxygen and determine that it's 63.01 grams per mole. 63.01 grams per mole. All right, so now we look at the mass of each one of these elements relative to the whole thing. So for hydrogen, we have a single hydrogen, so 1 times 1.008 grams per mole divided by the whole thing, 63.01 times 100. So if we do that, hydrogen will be 1.60%. And I know I brought it down to 3 sig figs, but I could have, that's just because I chose 4 sig figs, but anyway, that's where my answer is right now. Nitrogen, there's 1 nitrogen. So for nitrogen, we have 1 nitrogen. It has the mass of 14.01. So we compare it to the mass of the whole thing and multiply it by 100. And so nitrogen's mass would be 22.2%. And then lastly, we have oxygens, specifically 3 of them. So there's 2 ways we can do it. I'll show you both. We could say 3 oxygen. Each oxygen weighs 15.999. So we divide the mass of the 3 oxygens by the mass of the whole thing, multiply by 100, and we would get 76.2%. Or we could have simply said 100% minus 1.60% minus 22.2%. Either one of these would work for oxygen. And they should give you pretty much the same answer. So whichever way you want to use, just make sure you show your work. And then lastly, tungsten 6 oxide. Again, good reminder that you have to have the right nomenclature to get these right. Tungsten is W, believe it or not. It's got a +6 charge, oxide's 2 minus, so tungsten 6 oxide would have that formula. And once you know it's that formula, you could calculate that it would have a mass of 231.84 grams for every mole. And again, that's from the periodic table, 1 tungsten and 3 oxygen. All right, so the mass of the tungsten, W, tungsten's mass on the periodic table, it's right here, is 183.84. So I'm going to compare that to the mass of the whole molecule and make it a percentage by multiplying by 100. And I get 79.3%. For the oxygen, this time, I'm just going to say it would equal 100% minus 79.3%, which would equal 20.7%. And before you guys get all crazy about sig figs, when I say 100%, I can mean it as 100.00000%. So don't worry about the fact that I put a decimal place past that after I subtracted. All right, so that is how you do percent composition when you are just given a formula or a name and then a formula. Okay, so again, if I have, miraculously, if I have enough time, I'll do some more of those, but it would take a miracle. So I want to move on to the newer stuff. Okay, so I could read you this, or you could sit there and read the glossary type definitions of molar or of empirical formula and molecular formula, and I'll get back to that, but let me just show you what it is, and then it'll probably make total sense. So this is glucose. This is the molecule glucose. And you know, or we've mentioned before, it's C6H12O6. Well, you might look at that and say, well, this is the actual formula for glucose. It has 6 carbons, 12 hydrogens, 6 oxygens. But you might say, well, you know what? What if I simplified this and divided through by 6? The actual ratio of carbon to hydrogen to oxygen, the simplest ratio, is 1 to 2 to 1. So this is the simplest ratio, as I've written up there. This is the actual quantity. So that's the difference between an empirical formula and a molecular formula. This molecular formula, C6H12O6, that is what glucose is and will always be. This represents just the ratio of carbons to hydrogen to oxygen within that molecule, and that's called the empirical formula. Now, what we're about to embark on the next few slides will leave your wrists sore. I get this, but it's going to be ultimately a lot of math, but it's, well, anyway, yeah, dig in is what I'm saying. We're about to cover that, both empirical and molecular formulas. All right, so let's start off by describing this experiment. This experiment saw someone take half a gram of scandium. So they had 0.5 grams of scandium. And then it says they were allowed to react it with oxygen from the air. Okay, so it reacted and it formed a scandium oxide. Okay, so what they're saying is they heated it up and then they added O2. It had O2 around it, and then somehow in that process it formed an oxide. Now scandium, oxygen Y. Scandium is a transition metal. So we don't know what the charge is. We can't, if it was calcium, we'd say, oh, it's +2, so it would just be calcium CaO, calcium oxide. But we don't know what the charge of scandium is. It could be a variety of things. So we're going to have to figure it out. Now, the only other piece of information is that we got 0.767 grams of product. All right, so the first thing I need to point out is that moles and mass are two different things. And you probably had caught that the first time, but let me point something out here. Here's an easy molecule we all know, H2O. This means that there are 2 atoms of hydrogen to 1 atom of oxygen. But what it does not mean, and I can't stress enough, is that this is not 2 grams of hydrogen to 1 gram of oxygen. That's mass. Oxygen weighs a lot, and oxygen weighs 16 grams per mole, hydrogen weighs 1 gram per mole. So this is not the ratio by mass, this is the ratio by number. Now, when we deal with things in a laboratory, we weigh them and we get mass. But we can't, again, use mass to construct formulas. We can only use the number of compounds. So when you think of number and quantity, think moles. Because what I need to figure out is how many scandiums reacted with how many oxygens. Not their masses, their quantities. So that's why I need moles. So what I'm going to do is I'm going to take my 0.5 gram of scandium and I'm going to convert that to moles. So 1 mole of scandium, if you look it up on the periodic table, is 44.96 grams. So if I have 0.5 gram of scandium, you would compute that you had 0.111 moles of scandium. Now, this is a quantity. This is a mass. A quantity, I can compare ratios, like 2 to 1 or 1 to 2 to 1. And that's why moles are so powerful, because they're a quantity. What I need is the quantity of oxygen, or the moles of oxygen. So I need to know the grams of oxygen that I have. Well, I didn't add it myself. I just allowed the scandium to burn in air, and I can see what the final mass is when it added oxygen. So it went from scandium to scandium with some number of oxygen on it, and it gained a little mass. So the mass it gained was oxygen. And the mass gained was the mass of the product minus the mass of the original reactant, or 0.267 grams of oxygen. So I now have my mass of oxygen, 0.267 grams of oxygen. Now I know there's going to be a hand about to go up, so I'll address that in a minute. The hand that's going to go up will ask me, why did I not say O2 and why did I not put O2 and have 32 grams per mole here? And if you didn't think to ask that question, you might think by the time you watch this video. So the issue is we have O2 adding, and when you have oxygen, O2 is elemental oxygen. It's an oxygen atom double bonded to another oxygen atom. And even if you don't know what that means, realize that that has to be split apart. And then these oxygen atoms now go on to form compounds. So yes, elemental oxygen as it started out is O2. But how it ends up when it's part of a compound are individual oxygen atoms in that compound, just like we have an individual oxygen in water. So if it's O2 by itself, it's O2 32 grams per mole. If it's part of a compound, we're just talking about oxygen in general, and it's 16 grams per mole. But regardless, when we calculate the molar or the moles of oxygen, we get that. So we knew the mass of scandium relative to the mass of oxygen. Now we know the quantity of scandium relative to the quantity of oxygen. And they're very different numbers because they're very different. So we would have scandium, if we were writing our our formula, we'd have scandium 0.0111, oxygen 0.0167. Because we can do that, because these are numbers. The ratio, we're constructing a ratio. But this probably looks really odd because you can't have anything other than whole numbers. You can't have a portion of an atom, right? It'd be like going to the store and saying, yeah, I only have, I know this is only 10 cents. I only have a quarter. Let me break off a piece of this quarter and give it to you. I'm not going to take a part of a quarter. You give me the whole thing or not, right? Well, atoms are like that. They only come in whole number ratios. So we need whole numbers here, counting numbers. So how we convert this to counting numbers, and we're going to do this a lot over the next 10, 15 minutes, is we take the smaller of the two numbers and we divide it into both of the numbers. So between the two of these, this is the smaller number. So what I'm going to do is divide both of them by that smaller number. And when I do that, any number divided by itself will be 1. When I divide oxygen's number by 0.0111, I get oxygen 1.5. All right, well, we're getting closer to counting numbers, but I still can't have 1.5 oxygen. There's no such thing as half of an oxygen molecule. So I might say, well, I could round up to 2, but you could just as easily round down to 1. But there's an even better approach. Does anyone have an idea how I would make this a nice round counting number? Yeah, times it by 2. So I'm going to multiply this whole thing by 2 and make it scandium 2, oxygen 3. Perfect whole number ratios. So yeah, it turned out that it was scandium 3 oxide. And this is how we figured it out. And this is the empirical formula. All right. So if you are looking at this going, oh my gosh, my eyes are glazing over, bring yourself back. We got lots of problems to do. And your wrist will get sore. So this is your go-to page. If you know this already and you're just going through the motions, fine. If this is the first time you've heard it, this will be your go-to page to figure out how to solve them, because even though it's long and complicated, you can follow the same methodical procedure each time and always get the right answer. And this will show you how to do it. Oh, thank you. Okay, so when you're given a problem, and I'll come back to this problem, but let me just peek at the next one. Oftentimes you're given the percentages of the different elements that are determined. So let's go back to the problem we're working on that will show us how to do it easily. The very first thing you do when you're given those percentages is literally take that percentage sign, cross it out, and turn it into grams. So you can see that's all that changed from one pie chart to the next. I took the percentage, crossed it out, and made it grams. Now the reason why that's legal is because percentage means out of 100 equals out of 100. So we assume that whatever sample we have, whatever this compound was, we just assume we had 100 grams of it. So if we had 51.41% of 100 grams, well, it'd be 51.41 grams. So that's why it's legal. Okay, so we've taken our percentages, we've changed them to grams. Now we take those grams and we convert to moles. So that's what we did, or we're working on this week a lot, is looking up the molar masses and converting to moles. So it's good work for this chapter. So if we have 42.12 grams of carbon, 1 mole of carbon is 12.0 grams. Now, the reason why I'm limiting the number of sig figs, because I could have used all of these sig figs, is because our numbers that we're getting for our empirical formula are like 1 sig fig, right? So having 5 or 6 sig figs is a little overkill and will take a long time. So for these problems, having 3 sig figs is fine. All right, so that's my carbon, my oxygen, my hydrogen, we'll just go in order here. I'd have 6.48 grams of hydrogen, and 1 mole of hydrogen is about 1.01 grams. I have 51.41 grams of oxygen. 1 mole of oxygen is 16 grams. So all I've done again is taken my grams and I'm dividing by the molar mass that I would get from the periodic table. And when I do that, I get 3.51, 6.42, and 3.21. This is moles of carbon, this one's moles of hydrogen, this one's moles of oxygen. Okay, so started with percentages, changed to grams. Grams, I converted to moles. And by the way, if you get used to saying, what do I do with my grams? And you say convert to moles, that's probably going to be the right answer for the next 3 weeks. Okay, so we take our grams and we convert to moles, then we do our simplified formula. And that means that we take these numbers that we've gotten and we make a messed up looking formula with them. 3.51, 6.42, 3.21. So that's where we do that. And then you say to yourself, I can't have decimals or fractions. I have to divide by the smallest of all these numbers, which would be the 3.21. And when you do that, you will get C1.09, H2, oxygen 1. Now, these are perfect. This one here, it's within about 10% of the closest whole number. So that's an example where it's okay to round. So we would just call this carbon 1, we don't need the 1, H2O1, but we don't put the 1s. So this would be the empirical formula based on the data that was given. So this is what we're going to do every single time, this exact same process. So this is your go-to flowchart for how to solve any of these problems for empirical formulas. So let's try it. So glycine's an amino acid. At a certain point, they didn't know what its formula was, so they had to start out by determining its empirical formula. So they burned glycine and they figured out that its elements were in these following percentages. You don't care about that. You probably just say, all right, how do I solve this problem? So the first thing you do is you take the percentages and do what? Just change it straight to grams. So you take the 32% carbon, we say 32 grams of carbon, and we do that for every single thing. All right. Now if you have grams of the different elements, what do you do with the grams? Convert to moles, right. And so if I say what do you do with grams of something, like if you just say convert to moles, you're right, probably 95 times out of 100. Okay, so again, we're not going to need a whole bunch of sig figs, so we can make this a little quicker for ourselves and use simpler numbers just like 12, or 1 mole of hydrogen would be 1.01 grams. And again, these numbers I'm getting from the periodic table. 1 mole of nitrogen is 14 grams, and then 1 mole of oxygen is 16 grams. Okay. So, get these ahead of time. We get 2.67 moles of carbon, 6.6 moles of hydrogen, 1.34 moles of nitrogen, and 2.66 moles of oxygen. Okay, so percentages to grams, grams divided by molar mass to moles, and now we take these moles and we use them and make a messed up looking formula. Carbon 2.67, hydrogen 6.6, nitrogen 1.34, oxygen 2.66. Okay, and then we need to convert this to our simplest whole numbers. So we find the smallest of these values and divide it into every single value. So that would be the nitrogen. And when we simplify it, you'll get carbon 1.99, hydrogen 4.93, nitrogen 1, oxygen 1.99. So I would imagine most, if not all of you, are comfortable with me simplifying this, rounding carbon up to 2, rounding hydrogen up to 5, nitrogen is already 1, and oxygen would easily round up to 2. And that would be our empirical formula for glycine. Now, glycine might have its actual structure might be one multiple of this. There might be that conversion factor, like we had with glucose. But anyway, this is the empirical formula. All right. So, remember a little while ago, like maybe about 10 minutes ago, it might seem like a year ago, I said you might have a molecule like C6H12O6, and you could say, all right, I know its empirical formula would just be CH2O. But what if you determined the empirical formula and you wanted to go back to figure out what the actual molecular formula was? How would you know that you needed to multiply this by 6 to get it back to its formula? Well, that times 6 is called a conversion factor. And the way you determine it is you divide the molecular mass divided by the empirical mass. And I'll, of course, say what I mean. The molecular mass is the mass of the molecule when it has all of its parts. And that is going to be given to you in the problem. So in this example, they say that glucose is 180 grams per mole. I have determined at this point that the empirical formula is CH2O. And if I just quickly add this up, again, remember the conversion factor we know is 6. We know that's what it's going to be, but if we didn't, this is how you'd figure it out. That's only 1 sig fig. So when I add this up, I can just be kind of hasty about it and go, okay, carbon's about 12, hydrogen's about 1, and there's 2 of them, and oxygen is about 16. So I'd say, okay, this would equal about 4 equals about 30. About 30 grams per mole. And again, my conversion factor is only 1 sig fig, so I'm not worrying a whole bunch about sig figs here. 2 sig figs, 30 grams per mole. So that's my empirical mass. I don't even need the point there, it's 30. So my conversion factor, when you divide 180 by 30, equals 6. And that's the conversion factor. So that's how we would have determined that we would have taken our empirical formula, multiplied it by 6, and the actual formula is C6H12O6. So this next problem walks through the entire process of determining the empirical formula, then using the molar mass of the molecular formula, and then determining that. So this is the whole kit and caboodle. This is the whole thing in one problem. And so, yeah, you might get an exam. It could be a final. It could be the collaborative. It could be your chapter exam. You're going to have a problem like this. You're going to do all the work. You'll bubble in your little bubble, and it'll be worth exactly the same amount of points as the one that said 6.022 equals blank's number. And you're like, oh, Avogadro's number. They're going to be worth exactly the same. But this one's going to be a lot of work. Okay. So let's, hey Jeff, almost. Last slide. Okay. Yeah, see, he's excited about the demo too. So yeah, don't forget about that demo. So I know your wrists are going to be tired from this, but there's definitely light at the end of the tunnel. Okay, so let's do this. We take our percentages and what do we do with them? Change to grams. All right, so what we have is 12.7 grams of carbon, 2.1 grams of hydrogen, and 85.1 grams of bromine. That's what we really have. All right, then we take our grams and do what with them? Convert to moles. So we take that and we say, all right, 1 mole of carbon, 12 grams. 1 mole of hydrogen, 1.01 grams. 1 mole of bromine, I don't have memorized, 79.9 grams. All right, so when I crunch these numbers, and I'm hopeful I did them right, first time 1.06 moles of carbon, 2.08 moles of hydrogen, and 1.07 moles of bromine. All right, now you make your messed up formula, your messed up looking formula, C1.06, H2.08, bromine 1.07. Then we divide by the smallest. And this will simplify to carbon 1, hydrogen 2 divided by 1. Hopefully you can see that that's going to be a 2. And then basically the same number divided by itself will be 1. So this is our empirical formula. And that's part of what it asked us to solve for, the empirical formula. All right. But that's not what the actual formula for ethylene dibromide. We don't know what the actual formula is. We need to get a conversion factor. So this is for part B. The conversion factor is equal to the molecular mass divided by the empirical mass. The molecular mass will always be given in the problem in this class, 190 grams per mole. The empirical mass is the mass of our empirical formula. So that would be, and again, you can kind of be simple with your digits. That's 12 for the carbon, plus 2 times 1 for the hydrogen, plus 79.9, we'll just call that 80, plus 80 for the bromine. So again, I know I'm not using a ton of sig figs, but our conversion factor is only going to be 1 sig fig anyway. So 12 plus 2 is 14, plus 80 is 94. So this is 94 grams per mole. So when I do 190 divided by 94, I get 2.02. And that's our conversion factor. But remember, we can only have whole number ratios, so you probably are okay with me rounding that to just 2. So now I have to multiply